we've successfully made data centers into cloud computing over the past 20 or 25 years, where most people who use and consume data centers never actually see them or touch them. And so it's kind of out of sight, out of mind in terms of the impacts of the latest and greatest hardware or refresh. What happens to a 2-year-old NVIDIA server, when it goes to die? Does anybody really know?
Hello, and welcome to Environment Variables, brought to you by the Green Software Foundation. In each episode, we discuss the latest news and events surrounding green software. On our show, you can expect candid conversations with top experts in their field who have a passion for how to reduce the greenhouse gas emissions of software. I'm your host, Chris Adams. Hello, and welcome to Environment Variables, the podcast where we explore the latest in sustainable software development. I'm your host, Chris Adams. Since this podcast started in 2022, we've spoken a lot about green software, how to make code more efficient so it consumes fewer resources, or runs on a wider range of hardware to avoid needless hardware upgrades, and so on. We've also covered how to deploy services into data centers where energy is the cleanest, or even when energy is the cleanest, by timing compute jobs to coincide with an abundance of clean energy on the grid. However, for many of these interventions to work, they rely on the next layer down from software, the hardware layer, to play along. And for that to work at scale, you really need standards. Earlier this year, the SSIA, the Sustainable and Scalable Infrastructure Alliance, joined the Green Software Foundation. So now there's a hardware standards working group, the HSWG, within the Green Software Foundation too. Today, we're joined by two leaders in the field who are shaping the future of sustainable software. Sustainable hardware. We've got Zachary Smith from Packet, formerly of Packet and Equinix, and Truong from Zootocor. We'll be discussing hardware efficiency, how it fits into the bigger sustainability picture, the role of the Open 19 standard, and the challenges and opportunities of making data centers greener. So let's get started. So Zachary Smith, you're alphabetically ahead of Mr. Truong. So can I give you the floor first to introduce yourself and tell you a little bit about yourself for the listeners?
Sure. Thanks so much, Chris. It's really a pleasure being here and getting to work with Mai on this podcast. As you mentioned, my name is Zachary Smith. I've been an entrepreneur primarily in cloud computing for, I guess it's about 25 years now. I went to Juilliard, I studied music, and ended up figuring that wasn't going to pay my rent here in New York City, and in the early 2000s joined a Linux-based hosting company. That really gave me just this full stack view on having to put together hardware. We had to build our own computers, rent data center space, oftentimes help build some of the data centers, connect them all with networks, travel all around the world, setting that up for our customers. And so I feel really fortunate because I got to touch kind of all layers of the stack. My career evolved to touch further into hardware. It just became a true passion about where we could connect software and hardware together through automation, through accessible interfaces, and other kinds of standardized protocols, and led me to start a company called Packet, where we did that across different architectures, x86 and ARM, which was really coming to the data center in the 2014-15 timeframe. That business was acquired by Equinix, one of the world's largest data center operators. And at that point, we really had a different viewpoint on how we could impact scale, work with the sustainability groups within Equinix as one of the largest green power purchasers in the world, and start thinking more fundamentally about how we use hardware within data centers, how data centers could speak more or be accessible to software users, which, as we'll kind of, I'm sure, unpack in this conversation, are pretty disparate types of users and don't often get to communicate in good ways. So I've had the pleasure of being at operating companies. I now invest primarily in businesses around the use of data centers and technology, as well as circular models to improve efficiency and the sustainability of products.
Cool. Thank you, Zachary. And Mike, can I give you the floor as well to introduce yourself from what looks like your spaceship in California?
Thanks, Chris. Yes. So pleasure being here as well. Yeah, Truong. I'm currently the CTO at ZeroCore, a small two-phase liquid cooling organization, very focused on bringing sustainable liquid cooling to the marketplace. Was very fortunate to cross over with Zach at Packet and Equinix, and have since taken my journey in a slightly different direction to liquid cooling. Super excited to join here. Come from, unfortunately, I'm not a musician by classical training. I am a double E by training. I'm joining here from California on the West Coast in the Bay Area from a little James Cook, Springer, Westphalia.
Cool. Thank you for that, Mai. All right, then. So my name is Chris. If you're new to this podcast, I work in the Green Web Foundation, which is a small Dutch nonprofit focused on an entirely fossil-free internet by 2030. And I'm also the co-chair of the policy working group within the Green Software Foundation. Everything that we talk about, we'll do our best to share links to in the show notes. And if there's any particular thing you heard us talking about that you're really interested that isn't in the show notes, please do get in touch with us, because we want to help you in your quest to learn more about green software and now green hardware. All right, then. Looks like you folks are sitting comfortably. Shall we start?
Let's do it.
All right, then. Cool. Okay, to start things off, Zachary, I'll put this one to you first. Can you just give our listeners an overview of what a hardware standards working group actually does and why having standards with like data centers actually helps? I mean, you can assume that our listeners might know that there are web standards that make websites more accessible and easier to run on different devices. So there's a sustainability angle there. But a lot of our listeners might not know that much about data centers and might not know where standards would be helpful. So maybe you can start with maybe a concrete case of where this is actually useful in helping make any kind of change to the sustainability properties of maybe a data center or a facility.
Yeah, that's great. Well, let me give my viewpoint on hardware standards and why they're so critical. We're really fortunate, actually, to enjoy a significant amount of standardization in consumer products. I would say there's working groups, things like the USB Alliance, that have really provided, just in recent times, for example, standardization, whether that's through market forces or regulation, around something like USB-C. Right, which allowed manufacturers and accessories and cables and consumers to not have, extra things or throw away perfectly good devices because they didn't have the right cable to match the port, right? And so beyond this interoperability aspect to make, these products work better across a, fairly intricate supply chain and ecosystem, they also could provide real sustainability benefits in terms of just reuse, okay? In data centers, we've done this amazing thing. And we can kind of unpack some of the complexities related to the supply chain. These are incredibly complex buildings full of very, very, very highly engineered systems that are kind of changing at a relatively rapid pace. But the real issue from my standpoint is we've successfully made data centers into cloud computing over the past 20 or 25 years, where most people who use and consume data centers never actually see them or touch them. And so it's kind of out of sight, out of mind in terms of the impacts of the latest and greatest hardware or refresh. What happens to a 2-year-old NVIDIA server, when it goes to die? Does anybody really know? You kind of know in your home or with your consumer electronics, and you have, this real waste problem. So then you have to deal with it. Not to put lithium-ion batteries in the trash. So you find the place to put them. But, when it's the internet and it's so far away, it's a little bit hazy for I think most people to understand the kind of impact of hardware and the related technology, as well as what happens to it. And so that's kind of like, I'm going to say, one of the challenges we have in the broader sustainability space for data center and cloud computing. One of the opportunities is that maybe different from consumer, we know actually almost exactly where most of this physical infrastructure shows up. Data centers don't move around usually. And so they're usually pretty big. They're usually attached to, pretty long-term physical plants. And there's not millions of them. There's thousands of them, but not millions. And so that represents a really interesting opportunity for implementing really interesting, which would seem complex models. For example, upgrade cycles or parts replacement or recycling or re-upskill, of hardware. Those things are actually almost more doable logistically in data centers than they are in the broader consumer world because of where they end up. The challenge is that we have this really kind of disparate group of manufacturers that frankly don't always have all the information or aligned incentives for making things work together. Some of them actually define their value by, did I put my logo on the left or did I put my cable on the right? You have a business model, which would be the infamous Intel TikTok model, which is now maybe NVIDIA. What's NVIDIA's version of this? I don't know, but it's kind of 18-month hardware refresh cycles are really, like put out as a pace of innovation, which are, I would say in many ways quite good, but in another way, it requires this giant purchasing cycle to happen. And people build highly engineered products around one particular set of technology and then expect the world to kind of upgrade everything around it. When you have data centers and related physical plant, where maybe 90 or 95% of this infrastructure can be very consistent. Things like sheet metal and power supplies and cables and, related. And so I think that's where we started focusing a couple of years ago, was how could we create a standard that would allow different parts of the value chain throughout data center hardware, data centers and related to benefit from an industry-wide interoperability. And that came to really fundamental things that take years to go through supply chain. And that's things like power systems, now what Mai's working on related cooling systems, as well as operating models for that hardware in terms of upgrade or life cycling, recycling. I'm not sure if that helps, but this is why it's a hard problem, but also why it's so important to make a reality.
So if I'm understanding, one of the advantages having the standards here is that you kind of get to decide where you compete and where you cooperate here, with the idea being that, okay, we all have a shared goal of reduce the embodied carbon in maybe some of the materials you might use, but people might have their own specialized chips. And by providing some agreed standards for how they work with each other, you're able to use, say, maybe different kinds of cooling for different kinds of chips without. Okay, I think I know more of this.
I think that's a good example. I mean, I would give a couple of very practical examples. Can we make computers that you can pop out the motherboard and have an upgraded CPU, but still use the sheet metal, the power, the cooling, the power supplies, et cetera? Is that a possibility? Only with standardization could that work. Some sort of open standard. And standards are a little bit different in hardware. I'm sure Mike can give you some color, having recently built our Open19 V2 standard. It's different than the software, right? Which is relatively, I'm going to say, quick to create and quick to change, and also different licensing models. But hardware specifications are their own beast and come with some unique challenges.
Cool. Thank you for that, Zach. Maya, I'm going to bring to the next question to you, because we did speak a little bit about Open19, and that was one thing that was a big thing with the SSIA. So as I understand it, the Open19 spec, which we kind of referenced, that was one of the big things that the SSIA was a kind of steward of. And as I understand it, there's already kind of an existing different standard that defines the dimensions of say a 19-inch rack in a data center. So, you need to be the same size and everything like that. But that has nothing to say about the power that goes in and how you cool it or things like that. I assume this is what some of the Open19 spec was concerning itself with. I mean, maybe you could talk a little bit about why you even needed that, or if that's what it really looks into and why that's actually relevant now, or why that's more important in, say, halfway through the 2020s, for example.
Yeah. So Open19, the spec itself originated from a group of folks starting with the LinkedIn organization at the time. Yuval put it together along with a few others. As that organization grew, it was inherited by SSIA, which became a Linux Foundation project. And so what we did when we became a Linux Foundation project is rev the spec. The original spec was built around 12-volt power. It had a power envelope that was maybe a little bit lower than what we knew we needed to go to in the industry. And so what we did when we revised the spec was to bring both 48-volt power, a much higher TDP to it, and brought some consistency to the design itself. So as you were saying earlier, TIA has a 19-inch spec that defines a rail-to-rail. but no additional dimensions beyond just a rail-to-rail dimension. And so what we did was we built a full, I'm going to air quotes, a mechanical API for software folks, right? So like, how do we consistently deliver something? You can create variation inside of that API, but the API itself is very consistent on how you go both mechanically bring hardware into a location, how you power it up, how do you cool it, allow for variations of cooling, but have a consistent API for bringing cooling into that IT asset. What it doesn't do is really dive into the rest of the physical infrastructure delivery. That was very important in building a hardware spec, was that we didn't go over and above what we needed to still consistently deliver hardware into a location. And when you do that, what you do is you allow for a tremendous amount of freedom on how you go and bring the rest of the infrastructure to the IT asset. So in the same way, when you build a software spec, you don't really concern yourself about what language you put in behind it, how the rest of that infrastructure, if you have like a communication bus, or is it like a semi API driven with a callback mechanism, you don't really try to think too heavily around that. You build the API and you expect the API to behave correctly. And so what that gave us the freedom to do is when we started bringing 48 volt power, we could then start thinking about the rest of the infrastructure a little bit differently when you bring consistent sets of APIs to cooling and to power. And so when we started thinking about it, we saw this trend line here about like, we knew that we needed to go think about 400 volt power. We saw the EV industry coming. There was a trend line towards 400 volt power delivery. But what we did inside of that hardware spec was we left some optionality inside of the spec to go and change the way that we would go do work, right? So we have some optional parameters to the infrastructure teams to go and change up what they needed to go do so that they could deliver that hardware, that infrastructure a little more careful or correctly for their needs. So we didn't overspecify in particular areas where I'll give you a counterexample. In other specifications out there, you'll see like a very consistent bus bar in the back of the infrastructure that delivers power. It's great when you're at hyperscale
so
scale.
Just stop you for a second there, Mike. The bus bar, that's the thing you plug a power, a thing instead of a socket. Is that what you're referring to there?
Oh, so good question there, Chris. So in what you see in some of the hyperscale rack at a time designs, you'll see two copper bars sitting in the middle of the rack in the back delivering power, and that looks great for an at scale design pattern, but may not fit the needs of smaller or more nuanced design patterns that are out there. Does that make sense? We deliver
so
power
instead of having like a typical kind of like three-way kind of kettle style plug, the servers just connect directly to this bar to provide the power. That's one of those
that's
bars
a bus bar.
is. Yeah?
That's correct. That's correct.
Gotcha.
Yes. Yep. And so we went a slightly different way on that, where we had a dedicated power connection per device that went into the Open19 spec. And the spec is up. I think it's still up on our SSIA.org website. And so anybody can go take a look at it and see the mechanical spec there. It's a little bit different.
Okay. All right. So basically, previously there was just a spec said computers need to be kind of this shape if they're going to be server computers in a rack. And then Open19 was a little bit more about saying, okay, if you're going to run all these at scale, then you should probably have some standards about how power goes in and how power goes out, because if nothing else, that allows them to be maybe somewhat more efficient. And there's things like, and there's various considerations like that you can take into account. And you spoke about shifting from maybe 48 volts to like 400 volts, and that there is efficiency gains by which we probably don't need to go into too much detail about when you do things like that, because it allows you to move along more power without so much being wasted. For example, these are some of the things that the standards are looking into, and in the last 10 years, we've seen a shift from data center racks, which use quite a lot of power, to some things which use significantly more. So maybe 10 years ago, you might had a cloud rack would be between 5 and 15 kilowatts of power. That's like, tens of homes. And now we're looking at racks which might be, say, half a megawatt or a megawatt of power, which is maybe hundreds, if not thousands of homes worth of power. And therefore you need, say, refreshed and updated standards. And that's where the V2 thing is moving towards, right? Okay, cool.
And Chris, I think one thing to add in there is just the hard thing about hardware standards, where the manufacturing supply chain moves slow. unless you are kind of the end-to-end verticalizer. Like some of the hyperscale customers can really verticalize. They build a data center, they build the hardware, they build lots of the same thing. They can kind of force that. But a broader industry has to rely upon a supply chain, maybe OEMs, third-party data center operators, because they don't build their own data center, they just use somebody else's. And so what we really tried to accomplish with V2 was allow for this kind of innovation within the envelope, and do one of our guiding principles was how could we provide the minimal amount of standardization that we would allow for more adoption to occur while still gaining the benefits. And so that it's a really difficult, friction point, because your natural reaction is to like solve the problem. Let's solve the problem as best we can. The issue is that injects so much opinion that it's very hard to get adopted throughout the broader industry. And so even things like cooling, well, single phase or two phase, full immersion or not, this kind of liquid or this way, different types of pressure, whatever. There's all kinds of implications, whether those are technology use, those are regulatory situations across different environments, So I think like that's the challenge that we've had with hardware standards, is how to make it meaningful while still allowing it to evolve for specific use cases.
All right. Okay. So I think I'm understanding a bit now, and like I'll try and put it in context to some of the other podcast episodes we've done. So we've had people come into this podcast from like Google, for example, or Microsoft, and they talk about all these cool things that they're entirely vertically designed data centers where they own the entire supply chain. They do all these cool things with the grid, right? But all those designs, a lot of the time these might be kind of custom designs in the case of Google, where no one gets to see them. Or in some cases, like say Meta or some other ones, it may be open compute, which is it's a different size to most people's data centers, for example. So you can't just like drop that stuff in. Like there's a few of them are out, but it's still 19 inches. That's the default standard in lots of places. And if I understand it, one of the goals of Open 19 is to essentially bring everyone else along who already have kind of standardized on these kind of sides, so they can start doing some of the cool kind of grid aware, carbon aware stuff that you see people talking about that you probably don't have that much access to if you're not already Meta, Google, or Facebook with literally research, R&D budgets in the hundreds of millions.
Yeah, maybe add some zeros there. Yeah, I think that absolutely, right, which is democratizing access to some of this innovation, right, while still relying upon and helping within the broader supply chain. For example, if EVs are moving into 400 volt, like we can slipstream and bring, that capability to data center hardware or supply chains, because the people making power supplies or components or cabling are kind of moving in those directions, right? But then it's also just allowing for the innovation, right? Like, I think we firmly believe, we've seen this in software. I think this is a great part of Linux Foundation, which is, no one company owns the, kind of monopoly on innovation. And what we really want to see was not to like, can we make a better piece of hardware, but can we provide, some more foundational capabilities so that, hundreds of startups or different types of organizations that might have different ideas or different needs or different goals could innovate around the sustainability aspect of data center hardware. And I think what we're focused on now within GSF is really taking that to a more foundational level. There's just a huge opportunity right now with the data center construction industry happening to really find a even more interesting place where we can take some of those learnings from hardware specifications and apply it to an even broader impact base.
Okay. All right. I'll come back to some of this because I know there's a project called Project Mycelium that Asim Hussain, the executive director of the Green Software Foundation, is continually talking about. But like we've spoken a little about, you mentioned, if I understand it, like this allows you to maybe have more freedom to talk about, maybe instead of having like tiny fans which scream at massive thousands and thousands of RPM, there's other ways that you could maybe cool down chits, for example. And like this is one thing that I know that the hardware standards working group is looking at, is finding ways to keep the servers cool, for example. Like, as I understand it, using liquid can be more efficient, quite a bit more efficient than having tiny fans to kind of cool at massive RPM to cool things down. But also, I guess there's a whole discussion about, well, there's different kinds of there's different ways of cooling things which might reduce the kind of local power draw, local water usage in a data center, for example. And like, maybe this is one thing we could talk a little bit more about then, because I don't know that much. We've had people talk about, say, liquid cooling and things like that before, as like, these are some alternative ways to more sustainably cool down data centers in terms of how much power they need, but also what their local footprint could actually be. But we've never had people who actually have that much deep expertise in this. So maybe I could put the question to one of you, like, let's say you're going to switch to liquid cooling, for example, instead of using itty bitty fans or even just slightly bigger fans running a little bit slower. Like, how does that actually improve it? Maybe I could put this to you, Mike, because I think this is one thing that you've spent quite a lot of time looking into. Like, well, yeah, where are the benefits? Like, how do the benefits materialize if you switch from, say, air to a liquid cooling approach like this?
Yeah, so on the liquid cooling front, there's a number of pieces here. The fans that you were describing earlier, they're moving air, which is effectively a liquid when you're using it in a cooling mode at 25,000 RPM. You're trying to move air across the surface, and it doesn't have a great amount of
heat transfer
heat removal and
capabilities.
rejection. Yeah, heat transfer capabilities, right? So in this world where we're not moving heat with air, we're moving it with some sort of liquid, either a single phase liquid like water or a two-phase liquid, and taking advantage of two-phase heat transfer properties. There's a lot of significant gains, and those gains really start magnifying here in this AI space that we're in today. And I think this is where Project Mycelium started to come into fruition, was to really think about that infrastructure end to end. When you're looking at some of these AI workloads, especially AI training workloads, their ability to go and move hundreds of megawatts of power simultaneously and instantaneously becomes a really, really tricky cooling challenge and infrastructure challenge. And so really what we wanted to be able to think through is, how do we go and allow software to signal all the way through into hardware and get hardware to help go and deal with this problem in a way that makes sense? So I'll give you a concrete example. If you're in the single phase space and you're in the 100 megawatt or 200 megawatt data center site, which is, this is kind of what XAI built out in Memphis, Tennessee. When you're going and swinging that workload, you are swinging a workload from 0 to 100% back to 0 quite quickly in the time scale of around 40 milliseconds or so. You can move a workload from 0 to 200 megawatts back down to 0. And when you're connected to a grid, all right, that's called a grid distorting power event, right? Like you can go swing an entire grid 200 megawatt, which is probably like maybe like a quarter of the LA area of like the ability to go and distort a grid pretty quickly. And when you're an isolated grid like ERCOT, this becomes like a very, very tricky proposition for the grid to go and manage correctly. On the flip side of that, like once you took the power, you created about 200 megawatt of heat as well. And when you start doing that, you have to really think about, what are you doing on your cooling infrastructure? If you're a pump-based system like single phase, that means that you're probably having to spool up and spool down your pump system quite rapidly to go respond to that swing in power demand. But how do you prep the system? How do you tell that this is going to happen? And this is where we really need to start thinking about these software hardware interfaces. Wouldn't it be great if your software workload could start signaling to your software or your hardware infrastructure, hey, I'm about to go and start up this workload, and I'm about to go and swing this workload quite quickly. You would really want to go signal to your infrastructure and say, yes, I'm about to go do this to you. And maybe you want to even signal to your grid, I'm about to go do this for you as well. You can start thinking about other options for managing your power systems correctly, maybe using like a battery system to go and shave off that peak inside of the grid and manage that appropriately. So we can start thinking about this once we have this ability to go signal from software to hardware to infrastructure and building that communication path. It becomes an interesting thought exercise that we can realize this is just a software problem. Like those of us that have been in this hardware software space, we've seen this before. And is it worth synchronizing this data up? Is it worth signaling this correctly through the infrastructure? This is kind of like the big question that we have with Project Mycelium. Like it would be amazing for us to be able to do this. And then the secondary effects of this is to really go think through. Now, if you're in Dublin where you have offshore power and you now have 1 hour resolution on data that's coming through about the amount of green power that's about to come through, it would be amazing for you to signal up and signal down your infrastructure to say you should really spool up your workload and maybe run it at 150% for a while, right? This would be a great time to go really take green power off the grid and drive your workload on green power for this duration. And then as that power spools off, you can go roll that power off, that power need off for a time window. So being able to think about these things that we can create between the software hardware interface is really where I think that we have this opportunity to really make game changing and really economy changing
okay.
Impact. So I have a viewpoint on that, Chris, too, which is like my TLDR summary is like infrastructure has gotten much more complicated, and the interplay between workload and that physical infrastructure is no longer, set it in there and just forget about it, and the fans will blow and the servers will work and nobody will notice the difference, in the IT room. These are incredibly complex workloads, significant amount of, our world is interacting with this type of infrastructure through software services. And it's just got more complicated, right? And what we haven't really done is provide more efficient and kind of advanced ways to collaborate between that infrastructure and the kind of workload. It's still working under some paradigms that data centers, you put everything in there and the computers just run. And that's just not the case anymore, right? I think that's what Maya was illustrating so nicely, is that workload is so different and so dynamic and so complex that we need to kind of step up with some ways for the infrastructure and that software workload to communicate.
I see. Okay, so I'll try and translate some of that for some of the listeners that we've had here. So you said something about, a 200 megawatt power swing. That's not that far away from 500,000 people appearing on the grid, then disappearing on the grid every 40 milliseconds. And obviously that's going to piss off people who have to operate the grid. But that by itself is one thing. And that's also a change from what we had before, because typically cloud data centers were known for being good customers because they're really, really flat, predictable power draw. And now rather than having a flat kind of line, you have something more like a kind of seesaw, like a sawtooth, up, down, up, down, up, down, up, down. And if you just pass that straight through to the grid, that's a really good way to just totally mess with the grid and do all kinds of damage to the rest of the grid. But what it sounds like you're saying is actually, if you have some degree of control within the data center, you might say, well, all this crazy spikiness, rather than pulling it from the grid, can I pull it from batteries, for example? And then I might expose that familiar flat pattern to the rest of the grid, for example. And that might be a way to kind of make you more popular with grid operators, but also that might be a way to actually make the system more efficient. So that's one of the things you said there. So that's one kind of helpful thing there. But also you said that there is a chance to kind of dynamically scale up power when there is lots and loads of green energy. So you end up turning into a bit more of a kind of better neighbor on the grid, essentially. And that can have implications for the fact that, because we're moving to, like you said, there's complexity at the power level, and it allows a data center to kind of, rather than make that worse, that can kind of address some of those things. So it's kind of complementary to the grid. Is that what you're saying? That's
I think you got it, Chris. You got it, Chris. Yeah. Exactly. So that's on the power side. I think that we have this other opportunity now that as we're starting to introduce liquid cooling to the space as well, we're effectively and efficiently removing heat from the silicon. Especially in Europe, this is becoming a very front and center conversation in data centers operating in Europe, is that this energy doesn't need to go to waste and be evacuated into the atmosphere. We have this tremendous opportunity to go and bring that heat into local municipal heat loops and really think about that much more in a much more cohesive way. And so this is, again, where we really, as Zach was saying, we really need to think about this a little bit more comprehensively and really rethink our architectures to some degree with these types of workloads coming through. And so bringing standards around the hardware, the software interface, and then as we start thinking through the rest of the ecosystem, how do we think through bringing consistency to some of this interface so that we can communicate workload is going up, workload is going down. The city needs X amount of gigawatt of power into a municipal heat loop. And how do we help the entire ecosystem out a little bit better? In the winter, probably Berlin or Frankfurt would be excited to have gigawatts of power in a heat loop to go and drive a carbon-free heating footprint inside of the area. But then on the flip side of that, going and building a site that expects that in the winter, but in the summer where you're not able to take that heat off, how do we think about more innovative ways of driving cooling then as well? Do we go and use that heat in a more effective way to drive a cooling infrastructure.
So, okay, so this is that. I'm glad you mentioned the example because I live in Germany and our biggest driver of fossil fuel use is heating things up when it gets cold. So that's one of the good ways to, like, if there's a way to actually use heat which doesn't involve burning more fossil fuels, totally, I'm all for that. There is actually one question I might ask actually is like, what are the coolants that people use for this kind of stuff? Because when we move away from air, you're not typically just using water, and so all these cases, there may be different kinds of chemicals or different kinds of coolants in use, right? I mean, maybe you could talk a little bit about that because I know that we had switches from when we've looked at how we use coolant elsewhere. There's been different generations of coolants and in Europe, I know one thing there's a whole ongoing discussion about saying, okay, if we're going to have liquid cooling, can we at least make sure that the coolants we're using are actually not the things which end up being massively emitting in their own right? Because one of the big drivers of emissions is like end of life refrigerators and things like that. Maybe you could talk a little bit about like what your options are if you're going to do liquid cooling and like what's on the table right now to actually do something which is more efficient, but is also a bit more kind of non-toxic and safe if you're going to have this inside a given space.
Yeah. So in liquid cooling, there's a number of fluids that we can use. The most well understood of the fluids is used both in the facility and the technical loop side is standard deionized water, just water across the cold plate. There's variations that are used out there with the propylene glycol mix to manage microbial growth. And the organization that I'm part of, we use a two-phase approach where we're taking a two-phase fluid and taking advantage of phase change to remove that heat from the silicon. And in this space, this is where we have a lot of conversations around fluids and fluid safety and how we're thinking about that fluid and end-of-life usage of that fluid. Once you're removing heat with that fluid and putting it into a network, traditionally, most of these heat networks are water-based heat networks where you're using some sort of water with a microbial treatment and going through treatment regimes to manage that water quality through the system. So this is a very conventional approach. Overall, there's good and bads to every system. Water is very good at removing heat from systems. But as you start getting towards that megawatt scale, the size of plumbing that you're requiring to go remove that heat and bring that fluid through becomes a real technical challenge.
And also, if I'm not mistaken, also there's challenges if you're not doing a two-phase approach to actually removing heat at a hot enough temperature that you can use it for something else, right?
Correct, Zach. There's like a number of like very like technical angles to this. So as you're going down that path, Zach. So in single phase, what we do is we have to move fluid across that surface at a good enough clip to make sure that we're removing heat and keeping that silicon from overheating. The downside of this is like as silicon requires colder and colder temperatures to keep them operating well, their opportunity to drive that heat source up high enough to be able to use in a municipal heat loop becomes lower and lower. So let's say, for example, your best-in-class silicon today is asking for what's known as a 65-degree TJ. That's a number that we see in the silicon side. So you're basically saying, I need my silicon to be 65 degrees Celsius or lower to be able to operate properly. The flip side of that is you're going to ask your infrastructure to go deliver water between 12 to 17 degrees Celsius to make sure that that cooling is supplied. But the flip side of that is that if you allow for, let's say, a 20 degrees Celsius rise, your exit temperature on that water is only going to be 20 degrees higher than the 17 degrees C inlet. So that water temperature is so low that for us to effectively move that heat, you're in a lukewarm shower at best. So we have to spend a tremendous amount of energy then to bring that heat quality up so that we can use it in a heat network. And two-phase approaches, what we're taking advantage of is the physics of two-phase heat transfer, where during phase change, you have exactly one temperature, which that
and phase change is going from a liquid to a gas.
Steam.
To a gas, exactly. Yeah. And so the easiest way, like we'll use the water example, but this is not typically what's used in two-phase technologies, is that water at an atmospheric pressure will always phase change about 100 degrees Celsius. It's not 101, it's not 99. It's always 100 degrees Celsius at atmospheric pressure. And so your silicon underneath that will always be at around 100 degrees Celsius or maybe a little bit higher, depending on what your heat transfer characteristics look like. And this is the physics that we take advantage of. So when you're doing that, the vapor side of this becomes like a very valuable energy source, and you can actually do some very creative things with it on two-phase. So there's like every technology is a double-edged sword, and we're taking advantage of the physics of heat transfer to go effectively and efficiently remove heat in two-phase solutions.
So I have one kind of question about the actual, how that changes what a data center feels like to be inside, because I've been inside data centers and they are not quiet places to be. Like, I couldn't believe just how uncomfortably loud they are. And like, if you're moving away from fans, does that change how they sound, for example? Because even if you're outside some buildings, people talk about some of the noise pollution aspects. Does a move to something like this mean that it changes some of it at all?
Oh, yeah.
Inside of the white space, absolutely. Like, one of the things that we fear the most inside of a data center is dead silence. And you might actually be able to end up in a data center where there's dead silence very, very soon with
that being a good
zero
thing,
air movement with no fans. Yeah. We'd love to remove the parasitic draw of power from fans moving air across data centers just to allow that power to go back into the workload itself.
So for context, maybe someone, if you haven't been in a data center, I mean, it was around, I think it felt like 80 to 90 decibels for me, which felt like do you folks have a, possibly could have been more, actually.
It's way more than that.
Yeah. So, I mean, it was if you have like if you have something on a wearable or on a phone, as soon as it's above 90 degrees, 90 decibels, that's like louder than lots of nightclubs, basically. Like, maybe there's so this is one thing that I felt, and this sounds like it does, like, it can introduce some changes there as well, rather than actually we're just talking about energy and water usage, right?
Yeah, most data center technicians wear ear protectors all the time, can't talk on the phone, have to scream at each other because it's so loud. Certainly, there's some really nice quality of life improvements that can happen when you're not blowing that much air around and spinning up multiple thousand RPM fans.
25 to 30,000 RPM fans will require you double hearing protection to be able to even function inside of the space. So there's a lot of energy there.
Oh, okay, cool. So these are some of the shifts that make possible. So the idea you might have data centers of which are able to be more active in terms of actually working with the grid, because for all the kind of things we might do as software engineers, there's actually a standard which makes sure that the things that we see Google doing or Meta talking about in academic papers could be more accessible to more people. That's one of the things that having standards for like Open 19 things might be, because there's just so many more people using 19-inch racks and things like that. That seems to be one thing. So maybe I could actually ask you folks, like, this is one thing that you've been working on, and you're obviously running an organization, ZooToCore here, and Zach, it sounds like you're working on a number of these projects. Are there any particular like open source projects or papers or things with really some of the more wacky ideas or more interesting projects that you would point people to? Because when I talk about data centers and things like this, there's a paper that's called the EcoViser paper, which is all about virtualizing power so that you could have power from batteries going to certain workloads and power from the grid going to other workloads. And we've always thought about it as going one way, but it sounds like with things like Project Mycelium, you can have things going the other way. Like, for people who are really into this stuff, are there any good repos that you would point people to, or is there a particular paper that you found exciting that you would direct people to who are still with us and still being able to keep up with the kind of, honestly, quite technical discussion we've had here?
Well, I would, not to tout Mai's horn, but, reading the Open 19 V2 specification, I think, is worthwhile. Some of the challenges we dealt with at a kind of server and rack level, I think, are indicative of where the market is and where it's going. There's also great stuff within the OCP Advanced Cooling working group. And I found it very interesting, especially to see some of what's coming from hyperscale, where they are able to move faster through kind of a verticalized integration approach. And then I've just been really interested in kind of following along the power systems and related from the EV industry. I think there's, that's an exciting area where we can start to see, data centers not as buildings for IT, but data centers as energy, components. So when you're looking at, whether it's EV or kind of grid scale, kind of renewable management. I think there's some really interesting tie-ins that our industry, frankly, is not very good at yet. Most people who are working in data centers are not actually power experts from a generation or storage perspective. And so there's some just educational opportunities there. I've found just as one resource, I don't know if they have it at the 7x24 conference group, which is the critical infrastructure conference, which everything from like water systems, power systems to data centers, has always been really a great learning place for me. But I'm not sure if they have a publication that is useful. We have some work to do in moving our industry into transparent Git repos.
Chris, my favorite is actually the OpenBMC code base. It provides a tremendous gateway where this used to be a very closed ecosystem, and very hard for us to think about being able to look through a code repo of a Redfish API and being able to rev that spec in a way that could be useful and implementable into an ecosystem has been like my favorite place outside of hardware specifications like Open19v2.
Okay, so I might try and translate that because the BMC thing, this is basically the bit of computing which essentially tells software what's going on inside a data and how much power it's using and stuff like that. Is that what you're referring to? And is OpenBMC like something that used to be proprietary? There is now a more open standard so that there's the visibility that wasn't there before. Is that what it is?
Right. That's exactly right. So you always have to, in years past, had a closed ecosystem on the service controller or the BMC, the baseboard controller module inside of a server. And being able to look into that code base was always very difficult at best and traumatic at worst. But having OpenBMC reference code out there, being able to go look and see an implementation and port that code base into running systems has been very, very useful, I think, for the ecosystem to go and get more transparency, as Zach was saying, into API-driven interfaces. But what I'm seeing is that prevalence of that code base now showing up in a number of different places, and the patterns are being designated into, as Zach was saying, power systems. We're seeing this become more and more prevalent in PowerShells, power control, places where we used to not have access, or we used to use programmable logic controllers to drive this. They're now becoming much more software ecosystem driven and opening up a lot more possibilities for us.
Okay, I'm now understanding the whole idea behind Mycelium, like roots reaching down further down into the actual hardware to do things that couldn't be done before. Okay.
Got it.
This
just one
now
layer
makes a lot
more.
sense.
Peel it back, one more layer.
Okay, stacks within stacks. Brilliant. Okay, this makes sense. Okay, folks. So thank you very much for actually sharing that and diving into those other projects. We'll add some, if we can, we'll add some links to some of those things, because I think the OpenBMC, that's one thing that is actually in production in a few places. I know that Oxide Computer use some of this, but there's other providers who also have that as part of their stack now that you can see, right?
We also put it into production when we were part of the Packet Economics team. So we have a little bit of experience in running this technical base in real production workloads.
Oh, wow. I might ask you some questions outside this podcast, because this is one thing that we always struggle with, is finding who's actually exposing any of these numbers for people who are actually further up the stack, because it's a real challenge. All right. Okay, we're coming up to time. So I just want to leave one question with you folks, if I may. If people have found this interesting and they want to follow what's going on with Zach Smith and Truong, where do they look? Where do they go? Can you just give us some pointers about where we should be following and what we should be linking to in the show notes? Because I think there's quite a lot of stuff we've covered here, and I think there's space for a lot more learning, actually.
Well, I can't say I'm using X or related on a constant basis, but I'm on LinkedIn at ZSmith. Connect with me there, or follow. I post occasionally on working groups and other parts that I'm part of. And I'd encourage, if folks are interested, we're very, very early in this hardware working group within the GSF. There's so much opportunity. We need more help. We need more ideas. We need more places to try. And so if you're interested, I'd suggest joining or coming to some of our working group sessions. It's very early, and we're open to all kinds of ideas, as long as you're willing to copy a core value from Equinix. As long as you can speak up and then step up, we'd love to help. There's a lot to do.
Brilliant, Zach. And over to you.
LinkedIn as well. We'd love to see people here as part of our working groups and see what we can move forward here in the industry.
Brilliant. Okay. Well, gentlemen, thank you so much for taking me through this tour all the way down the stack into the depths that we as software developers don't really have that much visibility into. And I hope you have a lovely morning/day/afternoon, depending on where you are in the world. All right. Cheers, fellas.
Thanks, Chris.
Thanks so much.
Hey everyone, thanks for listening. Just a reminder to follow Environment Variables on Apple Podcasts, Spotify, or wherever you get your podcasts. And please do leave a rating and review if you like what we're doing. It helps other people discover the show. And of course, we'd love to have more listeners. To find out more about the Green Software Foundation, please visit greensoftware.foundation. That's greensoftware.foundation in any browser. Thanks again, and see you in the next episode.